Okay, now I want to talk about Simpsons Rule and how that works. And your textbook actually goes through the derivation, and we could do that as well. But the idea behind Simpsons Rule is instead of approximating using a rectangle, you can think of as 0 degree, or a trapezoid where we're using a line segment to connect the 2 points, which you can kind of think of as first degree, Simpsons Rule approximates the graph using a parabola. Now, because a parabola has 2 degrees of, 3 degrees, 2 degrees of 3 unknowns, the 3 coefficients, you actually have to use 3 points. So that's why the intervals all have to be even here. Let n be an even integer. And then the idea is you take your interval of 3 points. So here we have our a1, and then we'd have our x1 and our x2. And then we'd use those points to approximate the graph using a parabola. So we'd find the best fitting parabola that would fit over those 3 points and find the area beneath the curve. And then we'd do the same thing on our next pair of 3 points. So in this picture that would be x2, x3, and x4. And again, we approximate the graph using a parabola through those 3 points. So it might be, something like that. And again, we're estimating and finding the area beneath those parabolas, and so on all the way through the same number of points. So since you always need 3 points, we're always going from 1 to the next even number, an even number to the next one. And that's why our formula here calls for n to be even, so that we can get full parabola segments all the way through. And the actual formula is very similar to the trapezoid rule, except you notice now we're dividing by 3n instead of 2n. And then notice the pattern on the numbers. First and last numbers, just like in the trapezoid rule, only get used once. They only occur one time. But then the middle numbers, instead of being just 2 all the time, notice they alternate. You have 4s showing up. So any point that would have been a middle point, any odd subscript, like x1 or x3, actually gets counted 4 times in the formula. And then the other even guys, the 2, they all get counted twice. So you really have this pattern that you can just remember to keep the Simpsons rule straight. It's 1, 2, 4, 2, 4, 2, all the way through, finishing with 4, and then 1. Okay. So we'd like to look at just an example now using Simpsons rule to compute to approximate the area. So we've already done with the trapezoid rule for the integral of x squared, so we'll do that now for Simpsons rule. So we want to approximate the integral from 0 to 4 of x squared using Simpsons rule with n equals 4. Again, for Simpsons rule, n has to always be an even number. So we start, just like we did with the trapezoid rule, by forming our partition. Delta x would be b minus a over, we're doing 4 intervals, so it would be 4 minus 0 over 4, or 1. That leads to our partition values of x0 equals 0, x1 equals 1, x2 equals 2, x3 equals 3, and x4 equals 4. And it's just a matter of plugging those numbers into our formula. Simpsons rule says that the area is approximately b minus a over 3n evaluate f of 0. And we just remember that pattern. The first one's got a coefficient of 1. The next guy has a coefficient of 4. So 4f of 1, then 2. 2 times f of 2, and then 4 again, 4 times f of 3, plus, and then the last endpoint is always 1, so just f of 4. And now it's just a matter of computing those things. 4 minus 0 over 3 times 4 would be 1/3. So we're going to have 1/3, and then we evaluate. F of 0 is 0. F of 1 is 1 squared, which would be 4 times, or 1 squared, which would be 1 times 4 would be 4. F of 2, 2 squared would be 4 times 2 would be 8. And then 3 squared would be 9 times 4 would be 36. Plus 4 squared, which would be 16. So we just add all those up. 4 and 8 is 12, and 36 is 48. 48 and 16 is 64 over 3. And you might notice, hey, that's exactly the area. That's exactly the area. And turns out Simpsons Rule, because you're approximating using parabolas, is actually always going to give you the area for a second-degree polynomial. Is always going to give you the area for a second-degree polynomial. Okay. And our next example with Simpsons Rule is asking us to approximate the natural log of 7 using Simpsons Rule with n equals 6. And we'll recall the natural log, by its definition, is the integral from 1 to x, or in this case 1 to 7, of 1 over t dt. So we essentially want to approximate the interval, or the integral from 1 to 7 of 1 over t dt using Simpsons Rule. Okay, so we start again by finding our delta x and setting up our partition. Delta x, b minus a over n. Now I chose this so that delta x becomes real nice. So we're essentially going to have our partitioned into 6 values, delta x each being 1. So our partition values are just going to be 1, 2, 3, 4, 5, 6, and 7. And then it's just a matter now of using Simpsons Rule. The area is approximately b minus a over 3n and then we would evaluate f of 1 and then 4 times f of 2 2 times the next guy, f of 3 4 times the next guy, f of 4 plus 2 times the next guy, f of 5 plus 4 times the next guy, f of 6, and now we're at the end, so it'd just be plus f of 7. Okay, and it's just a matter of working all that out. Well, 7 minus 1 over 3 times 6 would be 6 over 18 would be 1/3. And then we just go through. F of 1 would be 1. Right, 1 over 1. Remember, our function is 1 over t. Remember, our function is 1 over t, or 1 over x. So evaluating it would be 1 over 1. Then we'd have 4 times 1 over 2 would be plus 2. 2 times 1 over 3 would be 2/3. 4 times 1 over 4 would be 1. 2/5. 4 times 6 would be 2/3. And finally we finish with 1/7. And when you add all those up, you'll get 617 over 315, which is approximately 1.9587. And if you compare that to the actual natural log of 7, comparing that to the actual natural log of 7, which is 1.9459. So at least in the nearest tenth, we're okay. We're within a tenth of the answer. And it's from that point on that we start to get a little off. But again, this is an approximation method. You can make it better by increasing the number of intervals. Okay? So those are some examples with Simpsons Rule.